So which means this capital X represent the frequency domain function and simple X represent the time domain function. So then we came to a kind of a conclusion like, so if you want to evaluate the Fourier transform of a particular time domain function xt, so you should be like you should have a kind of a thorough idea about the integrations. So then we focus our discussion not to go into the depth of these integrals. So we'll basically cover the concept by using these properties and simple integrations. So the conclusion is actually, if you want to find the Fourier transform of any given random function, so you have to solve this integral. So then you may come across with a different type of complex integration. So to avoid that, so our discussion basically focus on very small integrations plus the Fourier transform, which can be easily derived from the Fourier transform properties. So our discussion is basically focused on those two domains. So based on that, so I found couple of examples and I share the solutions as well. So I'll brief out couple of examples for your clarity. So if you went through this one, so you may have kind of a better idea. So if you have any questions, so just raise these questions during this session. So I'm referring this first example, exercise 1. So this exercise 1, you are given that the time domain function is ft, which is defined as cos omega naught t. So you are asked to evaluate the Fourier transform. So by looking at this one, if the function is x in time domain, the corresponding function in frequency domain is capital X. So then it means like you need to find f, j, omega. So hope it's clear. So if your function in time domain is denoted by simple x, this corresponding Fourier transform can be denoted by capital X. So likewise, if your function is ft in time domain, the corresponding Fourier transform would be capital F within bracket j omega. So then you need to evaluate this integral. Sorry, not xt, ft. Okay, so nothing else. So just replace this x terms with f terms. So ultimately you get this. So it means like you need to evaluate this integral to get this Fourier transform of f, simple f. So by look, okay. Yes, now, so how do you get this one? So xt is a ft is a kind of a cost function. So then if you directly apply or replace this ft with this cosine, you will basically get this kind of a product, cos omega naught t into e to the power minus j omega t. So this is the function you need to integrate with respect to t. So it's like that. So this is not that easy to integrate. I know that if you are coming from this physical science background, so you can do it easily. But otherwise, so for these the students basically came from this technology side, so they didn't study this type of integration. So what we can is, I don't know whether in your mathematics you may study those once you come into this university, but so what we can do is we can easily solve this by replacing this cosine term using complex exponential. So we know that any cosine term can be replaced with this form. J theta e to the power minus j theta divided by 2. So then we'll plug this substitution here. So then it's something like this. Your f j omega equals minus infinity to plus infinity. So that cos omega naught t would be now e to the power j omega naught t plus e to the power minus j omega naught t divided by 2. This is your cos term into e to the power minus j omega t. So you can further simplify this and split into two integrations. So you have half minus infinity plus infinity. Here you have like j omega naught t e to the power minus j omega naught t plus another half minus infinity plus infinity e to the power minus j omega naught t e to the power minus j omega t. So hope it's clear. We just multiply these two terms. So then, by looking at this, you can simply say that. So if you just think of this product, this integral, and if you map it with this one, so you can easily find out that this is actually Fourier transform of, so this is actually Fourier transform of e to the power j omega naught t. If your xt would be e to the power j omega naught t, so then the Fourier transform is like this, minus infinity to plus infinity integral. Here you have e to the power j omega naught t into e to the power minus j omega. So this is actually Fourier transform of e to the power j omega naught t. So this is actually, this is Fourier transform of e to the power minus j omega naught t. So by looking at this one, you can simply say that, so this is equals to half Fourier transform of e to the power j omega naught t plus half Fourier transform of e to the power minus j omega naught t. It's very simple. So then, so we don't need to worry about this evaluating this Fourier transform. So you can refer the Fourier transform tables. So from the Fourier transform table, you can find that e to the power j omega naught t is actually equals to 2 phi. So this is Fourier transform delta function omega minus omega naught. Okay, so this is a delta function. This is delta function. Or this unit impulse. Unit impulse. So e to the power j omega naught t can be represented using, this is your Fourier transform 2 phi unit impulse with a kind of a shift of omega naught. So this can be easily taken from this Fourier transform table. So you don't need to worry about, you don't need to derive it. So you can just pick it from the Fourier transform table and write it down. So then ultimately, so you have f j omega Fourier transform of simple ft is half 2 phi delta minus this plus 2 phi. So the minus j omega naught t, definitely this shift would be plus delta omega plus omega naught. So then once you simplify it further, so this become phi delta omega minus omega naught plus phi delta omega plus omega naught. Okay, so if you plot this, so it's something like that. Now this is your frequency. You put omega axis. So this is your omega axis. So this is the Fourier transform. So you have two delta function. One is shifted to the right hand side by omega naught. The other one. So this is actually appear here. The magnitude is phi. Here you have omega naught. So this is actually minus omega naught. And another phi here. So you have two delta functions. One is at omega naught, the other one is at minus omega. So this is the Fourier transform of a cosine signal. Okay. So by looking at this, you can simply say that if you have a kind of cosine or sinusoidal function, it basically maps to two impulses in frequency domain. So if it is a cosine or sine function or sine, this is mapped to two delta functions in frequency domain. So if you study this modulation and related concept, so this may be useful, because in these modulations actually what we do is we take a kind of a message signal and we basically mix it with a kind of a carrier frequency. So carrier frequency would be a kind of a cos omega naught t or kind of a sine omega naught t. So omega naught t represent the angular frequency of the carrier. So if this is the case, so this carrier basically converted into a frequency domain as these two impulses. So one is at frequency of omega naught, the other one is at frequency of minus omega naught. So these two are kind of mirror frequencies. So they are basically mirror frequencies. So one is here it's 0, one is omega naught. So the other one is minus omega naught, which is the mirror value of along this vertical axis. So these are two mirror frequencies. So this is the Fourier transform of this kind of cosine signal. So this is Fourier transform. I hope it's clear. Okay, what happens if your ft becomes a kind of a sine omega naught? So then definitely this, instead of this e to the power j omega naught t plus e to the power minus j omega naught t divided by 2t 2. So you can simply replace this with e to the power j omega naught t minus e to the power minus j omega naught t divided by 2j. So once you replace this, so we basically can obtain the Fourier transform of sine omega t is a j phi delta omega minus omega naught. So then the other way around. So if you draw the distribution, here it's omega, this is f j omega. You can just put like this. So it's minus j phi, it's plus j phi. So like this. So if you want, you can simply plot this mod f j omega or the magnitude and the angle separately. So if you want it, you can draw the magnitude and the phase separately. So how do you plot this magnitude and phase? You can simply say that. So here j omega is the magnitude of this delta component. So we can simply say that so that the magnitude would be plus phi and minus phi. Or else you can simply say that this way. So let's assume like this is A1 and this is A2. So the magnitude of A1, actually we can simply say that the phi. Magnitude of A2 also can be expressed as phi by assuming that or planning to accommodate this minus sign inside the phasor of the second term. So I'll put these magnitudes as same, A1 and A2 as phi, by planning to add this minus sign into the phasor of this. So then the angle of A1 becomes, here you have J. So J means actually, so what's the angle? So if you J phi, so this cos phi plus J sin phi then e to the power J phi by 2 cos phi by 2 plus J sin phi by 2. So cos phi by 2 is 0, sin by phi by 2 is basically 1. So then you can simply say that e to the power j phi by 2 gives the j. So this is equal to this. So then we can simply say that this is pi by 2 angle of a2, so we have minus sign, so it means like it's minus 5 by 2. So then if you draw these two things, so the magnitude would be something like that. The magnitude would be magnitude is your phasor. So the magnitudes are 5 and 5. It's omega naught minus omega naught. Phases. So you have 5 by 2 minus 5 by, so this is minus 5 by 2. So this is 5 by 2. This is omega naught. This is so this is just the Fourier transform. So this is basically the Fourier transform. You can just plot the whatever the complex values. So then you can simply come up with the magnitude separately and the phases separately, like here. Okay. So then this is the spectrum for the cosine. So see, like it's a kind of a real function. So it's a kind of a real function. See, it's a kind of a real function. It's a kind of a real function, but once it comes to the sine omega t, so this is basically a complex function. So you have j terms here. So you don't have j terms, so this becomes a real function. So this becomes a complex function. So then it means like, so we mostly use this cosine signals to modulate it, because we know that the Fourier transform will be a kind of a real function. So we can easily map it to the frequency domain in real frequency domain. Once you deal with sinusoidal, so it basically map to a complex domain in frequency. So then you have to treat the phase and magnitude separate. So rather make our process complicated, so we can basically use cosine functions to modulations and related stuff. So hope it's clear. If you have any questions, just so do you have any questions? So then assuming that it's clear, so we can move to the next. So this is exercise 3. Okay, so you are asked to evaluate the Fourier transform of this ft equals delta function. So so the easiest way is like, so for this case, if you ask to derive the Fourier transform of delta function, so here you can't use the table. Okay, so then no point of asking you to derive now. So you can't use the Fourier transform table. Either you have to use this fundamental integral format, or you can use kind of properties of other functions. So here we can easily apply the fundamental formula. So the Fourier transform, so I'll drop j for the time being. So it's equals to minus cos ft e to the power minus j omega t dt. So this is the definition of the Fourier transform. So we will use this one. So you plug this ft. So here it's become delta t e to the power minus j omega t dt. Then you can refer the properties of this delta function. So you may, if you go back to your notes and refer these properties of delta function, we know that. So if you have a delta kind of a function xt, and if you multiply this xt with delta t, so this delta t is basically defined only at t equals 0. So the rest of the values of t, the delta t would be 0. So here delta t is 0. And from here also delta t is 0. So this is defined only at t equals 0. So if you just multiply any function, any non-zero function with the delta t, the delta function or the unit impulse, so whatever the values outside this t equals 0 get suppressed to 0, because this functional value is basically multiply with 0. Here also this value multiply with this corresponding value of the delta. So it's basically 0. So then this is basically simplifies to xt into uh, so this is basically simplifies to here. This is the only place you can get a non-zero value. So the functional value is x0, and we have delta t here. So this is because of, so delta t is fine only at t equals 0. So other than the t equals 0, delta t function is basically 0. So then if you multiply any function with delta t, so it basically gives a single value which is actually at t equals 0. So this is basically discussed under this unit impulse. So then we can simply replace this block delta t. So this is your xt now. So instead of t, you can just put 0. See? So you can simplify xt to x0. So now this is your xt. So if you replace t with 0, you can easily get the value. So this is becomes delta t e to the power j0 means 1. So now your integral converts to this form. So what's the value of this? So this is again 1. Because we know that if you integrate your unit impulse from minus infinity plus infinity, so it gives 0, because this delta t or the unit impulse is basically developed from a kind of a rectangular pulse having a area of unity, area of 1. So that's why this integral converges to 1. So this is already discussed in the unit impulse. So just refer it. So this is basically derived from this. So you have a unit area rectangular pulse, and we then make this delta goes to 0. So then this delta goes to 0 means this amplitude, this is like this delta 1. So the amplitude goes up and the width is goes down. So ultimately you will have a kind of a delta function having amplitude of infinity, and still the area is 1 at t equals 0. Okay, so this is basically discussed. So then from minus infinity plus infinity delta t dt gives a value of 1. So then we can claim that, so the Fourier transform of this is 1. So this is valid for the other way as well. So if anything in frequency domain can be, for example, if you have k here, so you can simply say that this is k delta t. So k can be represented as k into 1. So then this, you can treat this constant separately. So it becomes a kind of a k times delta t. So likewise, we can use that property somewhere else in the content. So we'll move to the next. So this is actually already discussed several times anyway. So we'll use this rectangular path exercise 4. This is defined as this minus t plus t0 . So if you draw it, it's something like that. So this is time domain function. So this is your ft. So it's something like that. It's plus t, it's minus t, value is 1. So this is something like that. So this is your rectangular pulsing time domain. So this is a rectangular pulsing time domain. So then you need to evaluate the Fourier transform. Fourier transform. So you have to solve this integral. So by looking at this function, you can basically simplify this integral, because this function is defined only for the range of between minus t and plus t. So rest of the values of time, the function ft is 0. So then this integral can be simplified to minus t to plus t. Ft during this region or range, the ft is actually 1 e to the power minus j omega t t. This is actually e to the power minus j omega t divided by minus j omega minus t is equals to j omega t. So this can be replaced with sine function. If you put 2 here and 2 here, so then you can combine this 2j and this. So this is basically 2 times sine omega t. Here you have omega. So then if you want, you can convert it into a sinc function. Sinc x actually equals to sine x divided by x. So sine omega t. So if you put t here So this becomes sine omega t. So we'll leave. So then this becomes sin function. So this is sin function. So then if omega equals 2t times sin omega t. If you plot it, so you know that how to plot this sin function. So this is omega. So this is capital F omega. So it's something like that. So here it's 2t. So these values basically. So then the inner argument should be a product of or the multiplies of phi. So omega t should equals to n times phi. Multiplies of phi. So then from this you can simply say that omega equals n phi divided by t. So then the first value would be phi over t. So this is 2 phi over t. This is minus phi over t. This is minus 2 pi over t. So this is your, so now this is the time domain signal. So the corresponding frequency domain signal is this. So this is already discussed in the most of the sections, but anyway, so this is the Fourier transform of a rectangular path. It's a kind of a sin function in frequency domain. So last time we discussed about the duality property. So if your time domain function is a kind of a sinc function, so the corresponding frequency domain would be definitely a kind of a rectangular pulse in frequency. Based on duality, so you can argue that the response in time domain, if it is a low pass filter. So this is basically discussed last time. Okay. So then, yeah. So if you go to this exercise 5, exercise 5, so here it's defined, your ft is defined as this. 0. C is actually 1 minus t, 1 plus t. This is other ones. If you draw this one, so previously we discussed this kind of a function. This is the function we discussed before. This is a kind of a symmetric rectangular pulse. So what about now? F bar t. So 1 between 1 plus t. So this is t, 1 plus t would be some. This is 1 plus t. Here 1 minus t. So it means like we just add 1 for these two blocks. So this is basically 1 minus t. So how do you obtain this from this? This is basically if you shift ft by 1 unit, if you shift ft by 1 unit to the right hand side, 1 unit, so this is basically ef tilde. So then from this one, we can simply say that f bar t equals ft minus 1. So you take the original ft, which is a symmetric rectangular pulse over the vertical axis, and introduce a kind of a unit shift or shift it by 1 unit to the right hand side. So it basically gives the f bar t. So this is the shifted version. So this is ft shift by 1 unit to right hand side. So then you can evaluate the frequency domain response or the Fourier transform of this t bar. Either you can use the integral form or else you can use the shifting property. So you can use the shifting property. Shifting property. So the shifting property basically gives, if you have a shift, so that shift is reflected in frequency domain as e to the power minus j omega t naught. Minus j omega t naught is now 1. Plus the Fourier transform of original function. Okay. So this is the Fourier transform of ft of ft. So this is your ft. So this is already derived. So this is already derived. This is actually 2t sinc omega t. So then the Fourier transform of this f bar t is actually, so this shift time domain, we identify that this f bar t can be easily derived by shifting the original symmetric rectangular pulse by 1 unit to the right hand side. So that shifting in basically reflects in frequency domain as a kind of a prefactor, exponential prefactor. So if you remember these properties, it's basically reflect as a exponential prefactor. So then you can just write it. So this is equals to e to the power minus j omega 2t sinc omega t. So keep in mind, so this block affects to the phase spectrum. Why? E to the power minus j omega, if you take the magnitude, so this is basically 1. So the angle is actually omega. It's a plus or minus omega depending on the shift. So for the time being, just assume it's like minus omega. So then it basically introduces a kind of a linear trend or kind of a shift in addition to this one. So if you manage to evaluate the magnitude and phase, so for this time shift, basically changes phase response, not this one. So you can keep the magnitude response as it is and change the phase spectrum or phase response or the phase spectrum by introducing a time shift to that original function. So what happens actually? So if you want to add a phase shift, if you want to add a phase shift, so what you can simply do is introduce a time shift. So if you want to add a phase shift to the frequency domain, you can introduce a time shift to the time domain. Phase shift in frequency domain can be translated into a shift in time domain. So keep in mind this, if you want to have a kind of a frequency shift in spectrum, so you can just introduce a time shift. Okay. So hope it's clear. Any questions? Questions so far? Okay, so then if you don't have any questions, so we'll move to the exercise 6. So here, so you have ft, which is defined as an infinite sequence. K minus infinity plus infinity, ak e to the power j omega naught t. So if you observe this pattern, so this is actually Fourier series. If you remember, so this is actually Fourier series of f. So these are the Fourier series coefficients, and you basically convert into a kind of a infinite sum of complex exponentials. So these are complex exponentials. So these are complex exponentials. This is Fourier series coefficients. Okay. So now you are asked to evaluate the Fourier transform of this. Okay. So how do you apply? So we'll stick into the integral definition. So you can come with this f omega Fourier transform of this ft equals minus infinity to plus infinity k goes from minus in plus infinity ak e to the power j omega naught t k dt. This is your xt or ft. Sorry, I missed one term. So this is ft to the power j omega t dt. Okay, so this is EFT. Actually, this whole block represents EFT. So then we can do like this. So this integral is basically consider this integral is with respect to t. So the summation is basically index based on this k, not t. So then we can take this summation out because it's a kind of an independent index. So this integral is affecting to this time variable here. It doesn't affect to ak because ak is simply indexed by k. So here in this exponential term, this is the only part where you can impact to this integral. So then we can basically take this summation, this block out. So we can take this block out from the integral. So why it's, so this summation is basically independent of t. So it don't have any deal with the integration with respect to t. So you can bring this summation out from the integral. So then it's become like this. Sum k goes to minus infinity plus infinity ak. So this is independent of t. Then you can integrate it. So you have e to the power j omega naught tk e to the power j omega t dt. Okay. So this is actually, if you closely look at this, one. So this is Fourier transform of this quantity. Like in the delta function, we can easily write this as 2 phi delta omega minus. Now previously we have this omega naught only. Now we have, in addition to t, we have this k omega naught. So now it's become k omega naught. So then this is equals to k goes from minus infinity to plus infinity ak. We have 2 phi here. You can take this out or whatever. You can keep this 2 phi delta omega minus k omega naught. So what happens actually? So if you plot this one, what about k equals 0? We have 2 phi a0 at, so we have 2 phi a0 at 0. So omega naught, we have like 2 phi a1 at omega naught, 2 phi a2 at 2 omega naught, here minus omega naught. So we have 2 phi a minus 1, 2 phi a minus 2 and 2 omega. So likewise, you will end up with a kind of a infinite series of delta functions. So infinite series of delta functions. Okay. Infinite series of delta functions. this is already known, no? So for example, so initially we discussed the Fourier transform of this. Sorry, Fourier series of this. So the spectrum would be, if you remember, the spectrum would be here we have like this kind of a spectrum. So this is like 0, this is omega naught, 2 omega naught, 3 omega naught, minus omega, minus 2 omega. So kind of a discrete spectrum. So similarly, once you apply the Fourier transform, even we'll ended up with a similar pattern. So what I want to highlight here is, now initially we don't have any kind of idea whether this is a kind of a frequency domain representation, because we basically convert this ft into a series of e to the power j omega t. So we didn't have a kind of a clear-cut idea whether this Fourier series represent a frequency domain translation of this time domain quantity. Now feel like once you apply Fourier transform, it basically gives the spectrum. So this is the spectrum in frequency domain. So this is the spectrum in frequency domain. So you can simply map it like, now the Fourier series is basically converted to Fourier transform. You will have the similar pattern here. Okay. Okay, then do you have any questions? Okay, so if you don't have questions, so we'll stop it today for today. So next time we move to a new topic. So up to now we basically consider all the signals in continuous in time domain, in time. So next time we'll move to discrete in time. Discrete in time. So then, so up to now we basically discuss this kind of a signal. So from next week onwards we will discuss this kind of signal, discrete in time. Okay. Okay, thank you. So if you have any questions, so you just raise it through the discussion forum in the sim, so you can just drop an email. Okay, thank you.